Previously, we covered the core foundations. Now, in part 4, we tackle Earth and the Moon. Last time, we looked at Earth's atmosphere, the thin, layered shell that keeps this planet alive. Today we're stepping back further, because Earth doesn't travel alone. The core question for this episode: what is the Moon's relationship to Earth? And why does that relationship matter more than most people realize? Not just as a curiosity, but as something that has fundamentally shaped this planet's history, its stability, and quite possibly, its ability to support life at all. Most planets in the solar system have moons, some have dozens, but Earth's moon is unusual, not because it exists, but because of its size relative to its host planet. The moon is roughly 1/4 the diameter of Earth. That's not a small tag-along. That's a gravitational partner. And when you start pulling on that thread, the picture that emerges is genuinely surprising. This is Orbital Dispatch, and this is Earth. Episode 4. Section 1. The basics. What the moon actually is. Let's start with the fundamentals. The moon is Earth's only natural satellite, sitting at an average distance of roughly 384,000 kilometers away, though that varies because the orbit isn't a perfect circle. At its closest point, called perigee, it comes within about 356,000 kilometers. At its furthest, apogee, it stretches out to around 406,000 kilometers. Diameter, about 3,474 kilometers. Mass, roughly 1.2% of Earth's. Surface gravity, about 1/6 of what you'd experience here. If you weighed 70 kilograms on Earth, you'd weigh just under 12 on the lunar surface. Not weightless, just significantly lighter. The moon is tidally locked to Earth, meaning it rotates on its own axis, at almost exactly the same rate it orbits us. One side always faces us, the far side, not the dark side because both sides receive sunlight, was completely unseen by human eyes until the 7th of October, 1959, when the Soviet Luna 3 spacecraft flew past and returned the first photographs. What those images revealed was a strikingly different landscape from the near side. Far fewer of the dark volcanic plains called Maria, and a much more heavily cratered surface. Why the two sides look so different is still not fully explained. It remains one of the open questions in lunar science. Worth holding on to as we go through this episode. The moon isn't just an object in Earth's sky. It has actively changed what kind of planet Earth is. We'll come back to exactly how, and why a version of Earth without the moon might have been unrecognizable. Section 2. How the moon formed. So where did it come from? The leading hypothesis, well supported, though still a hypothesis, is called the giant impact hypothesis. Roughly 4.5 billion years ago, in the early solar system, a Mars-sized body collided with the proto-Earth. That object is sometimes called Theia. The collision was oblique, a glancing blow rather than head-on, and it threw an enormous quantity of material into orbit. Over time, that debris coalesced under gravity to form the moon. The evidence comes from several directions. Lunar composition is strikingly similar to Earth's mantle material. It's depleted in iron compared to Earth as a whole, which fits a scenario where both bodies had already separated their iron cores before impact. Isotopic analysis, looking at ratios of different forms of oxygen, titanium, and silicon, shows extremely close matches between lunar and terrestrial rocks, closer than you'd expect from two bodies that formed independently elsewhere in the solar system. It's not a perfect fit. Some of that isotopic data is almost too similar, which is actually difficult to explain if Theia was a genuinely separate body. Researchers are still working through that tension. For now, though, the giant impact hypothesis remains the best match for what we observe. One important consequence: the moon formed hot. Its early surface was likely a magma ocean. As it cooled, lighter minerals floated upward and formed the pale highlands visible today. The darker Maria came later, volcanic flooding of large impact basins, mostly between 3 and 1.2 billion years ago. Section 3. What the moon does for Earth. Here's where it gets interesting. This is the part I flagged earlier. The moon is not a passive fixture in Earth's sky. It's an active gravitational influence, and the consequences run deep. The most obvious is tides. The moon's gravity pulls on Earth's oceans, producing the tidal bulge we experience as high and low tide. The sun contributes too, but the moon's effect is roughly twice as strong, despite the sun being far more massive, simply because the moon is so much closer. Tides aren't just a coastal phenomenon either. Over geological time, they've driven ocean mixing, influenced sediment cycling, and may have played a role in the origin of life. Tidal zones offer environments where chemistry can concentrate, dry out, and restart repeatedly. The second effect is subtler and arguably more consequential. The moon stabilizes Earth's axial tilt. Earth's axis is currently tilted at about 23.4 degrees relative to its orbital plane, and that tilt is what gives us seasons. Without the moon's gravitational steadying effect, computer models suggest the tilt could vary chaotically, potentially swinging between near zero and greater than 80 degrees over millions of years. Near zero means almost no seasons. High tilt means polar regions receiving direct sunlight for part of the year and complete darkness for the rest. Either scenario would dramatically alter long-term climate stability. Whether that would have prevented life from emerging is genuinely uncertain. Life on Earth has proved remarkably adaptable. But stable, moderate seasons over geological timescales have almost certainly helped shape the conditions that allowed complex life, and eventually us, to develop. Third, the moon has been slowing Earth's rotation for billions of years. When Earth first formed, a day may have been as short as 6 hours. Today, it's 24. And the slowdown is still happening. Earth's day lengthens by about 1.4 milliseconds every century. As a consequence of the same tidal interaction, the moon is also gradually moving away from us, by about 3.8 centimeters per year. We know this with real precision because laser reflectors left on the lunar surface during the Apollo missions let us measure that distance directly. So, the moon has shaped Earth's rotation, stabilized its axis, stirred its oceans, and may have contributed to the conditions that allowed life to persist across billions of years. Subscribe so you do not miss it.